Welcome back. Today I'd like to talk to you a little bit about finding the length of curves. And this is really something that we've talked about before. Typically, we talk about this in Calculus 2. How do you find arc length? So let's just start by recalling. Let's recall in two variables. That arc length or length of a curve is typically calculated by the integral from a to b of the square root of 1 plus the derivative of the function, which I'll write as dy over dx, quantity squared dx. And if you're curious where this formula comes from, go back and watch my arc length video in Calculus 2, and I explain where we get this formula. But I could rewrite this if I think of x as being equal to t. Okay, so let me rewrite this formula where x is actually equal to t. So I could rewrite this as the integral from a to b of the square root of, now if x and t are the same thing, then dx over dt, well, x is t, so that's just dt over dt, which is 1. So that's just 1 squared plus dy dt squared dt, where x equals t. Okay, so if you think of x's and t's as being the same, then I have the exact same formula there. Okay, so we can see that length then is kind of like the change in the x direction with respect to t squared plus the change in the y direction with respect to t squared, and then we take the square root. Okay, so in other words, this is kind of the magnitude of the velocity that we talked about from last section, and we'll use that. But we can even use this same kind of thinking in 3 dimensions. This generalizes to the 3rd dimension. So in space, if we have r of t, which is equal to f of t times I plus g of t times j plus h of t times k, then the arc length of that vector valued function will be the following. Then the length of that vector valued function is going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared plus h prime of t squared dt. Okay, so we just take the derivative of each of the components individually, square them, and then take a square root. Another way of writing this, which is exactly the same, is the integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared dt. Okay, and if we wanted to be very fancy about this, we could say that that's the integral from a to b of the magnitude of r prime of t dt. All right, so in other words, length is actually equal to the integral of the magnitude of the velocity. All right, that's kind of interesting to think about for a little while. Or the magnitude of the velocity, of course, is what we call the speed. So if you integrate the speed over an interval from a to b, where a and b are measured in terms of the parameter t, not in x necessarily, but measured in terms of the parameter t, then you integrate the speed over that parameter and you get the length. That's kind of interesting to think about. So let's do an example here so we can see how this works. So an example, let's find the length. Of the curve r of t is equal to, let's say we have 2 sine t in the I direction plus 5t in the j direction plus 2 cosine of t in the k direction. And we'd like to find the length of that curve from -10 less than t less than 10. And I'll just go ahead and say less than or equal to for both of those. Okay, so for t ranging from -10 to 10. So if we want to set this up, the length will be the integral, and t is ranging from -10 to 10, so I put in from -10 to 10 of the square root of the derivative of each of the components squared. So the derivative, first of all, of my x component, which is 2 sine of t, the derivative of 2 sine t is 2 cosine of t, so I get 2 cosine of t quantity squared plus let's take the derivative of the second component. Derivative of 5t is just 5 quantity squared. And then the derivative of 2 cosine of t is -2 sine t quantity squared dt. Okay, let's simplify this a little bit. I have the integral from -10 to 10 of, let's see, we get the square root of, if I square this out, I get 4 cosine of t plus 25 plus 4, oops, this is squared, I'm sorry, sine squared of t dt. All right, and notice that 4 cosine squared of t plus 4 sine squared of t, I could put those two together and factor out a 4, and then I just get a cosine squared t plus sine squared t, which is 1. So 4 cosine squared t plus 4 sine squared t, or if I combine this guy and this guy, it just gives me 4. So I get the integral from -10 to 10 of the square root of, I have 25 plus 4, so 29 dt, which is equal to square root of 29 t evaluated from -10 to 10, which is equal to 10 root 29 minus -10 root 29, which is equal to 20 root 29, which is my answer. Okay, so we were able to find the length of this curve. Now, what's kind of amazing about this in some ways is, like, if you think about what we started with, this is a sort of complicated curve in 3 dimensions. okay? And we just said, okay, if as long as I know the parameterization, I can plug that into a nice arc length formula, and I can find the length of that curve. And it wasn't even really that hard to do. Now, the nice thing is that it actually did work out that I could simplify what I had right here. That's not always the case, and maybe we would have to do something a little more difficult in some situations, but we know the general process for finding the length of a three-dimensional curve. That's pretty cool. Okay. Now, let me write another definition. So let's say that we have a function s of t, which is equal to the integral from a to t of the magnitude of r prime of u du. This is called the arc length function. Okay, so and what's different between this and what we've been doing already? Not a lot, but there is one major thing, and that is that instead of integrating here from a to b, I'm integrating from a to t, where t itself is a variable. So I could plug in different values for t in this function and get different arc lengths. So this is a function, s of t, that gives me the arc length at any point t. Okay, so it's giving me a lot of arc lengths at the same time, not just one arc length. So plug in any value you want to for t in this function, and I'll get an arc length from a to t. And that's the point of the arc length function. All right? Now, the last thing that I want to go over with you is the arc length of a polar curve. Okay, so we've dealt with polar equations in the past. How do we find arc length of a polar curve? I don't know why I wrote A as a capital letter. I just felt like it, I guess. So arc length of a polar curve. So let's start with just our standard arc length formula. Okay. Our standard arc length formula would look something like this. That the length of a curve would be the following. Integral from, well, I'm going to write alpha to beta because typically we think of these things in terms, a parameter theta is what we use for polar, and so I'm just going to write things starting out in terms of theta. But theta can just be thought of as like a standard parameter. Theta is the same as a t, is the same as a z. I mean, really, it's just a letter. So I can write my arc length formula in terms of any letter I want to. Well, I want to write it right now in terms of theta. So I'm going to write dx d theta squared plus dy d theta squared d theta. And so I haven't really changed anything here. I've just replaced the x's in the, I've just replaced the t's in the equation with thetas, which is fine. It's just a variable. So I replaced all the t's with thetas. Okay, but now I've got this expression dx d theta. So the derivative of x with respect to the variable theta, and I've got dy d theta, which is the derivative of y with respect to the variable theta. But we know something about x and y when it comes to polar. I know that x is equal to r cosine of theta, and I know that y is equal to r sine of theta. So if we want to talk about the derivative of x with respect to theta, or the derivative of y with respect to theta, we can do that. Now, r may not be the best in this situation because typically r is a function of theta. So I could write r as f of theta cosine theta, and I could write y as f of theta, just some function of theta, times sine of theta, because I know that r really is standing for some function of theta. And now, if I wanted to take the derivative of x with respect to theta here, then I just use the product rule, and I get that it's the first thing, f of theta, times the derivative of cosine of theta, which is negative sine of theta, plus the second, cosine of theta, times the derivative of the first. So I get f prime of theta cosine theta. And then for the second piece, I get that dy d theta, same, I want to use the product rule. So I get f of theta times cosine theta plus f prime of theta sine of theta. And now what I want to do is let's take this dx d theta, plug it in up here. Let's take this dy d theta, plug it in right here, and let's just see what happens. Okay, so let's rewrite this, plugging in what these things are. So I get that the length is equal to the integral from alpha to beta of the square root of, okay, dx d theta squared. So I get f of theta times negative sine of theta plus f prime of theta cosine theta quantity squared plus f of theta cosine theta plus f prime of theta sine theta quantity squared d theta. Okay, and now I need to multiply this out. Okay, so what I'm going to do, I'm going to erase some of the stuff on top real quick so I can keep that on the bottom for so I can look at it. So what I'm going to do is let's just quickly erase some stuff up here. Erase. So now, so let's go back up, and I get that the length is equal to integral from alpha to beta of the square root of, now we need to square this out. So it's the first thing squared, so I get f of theta squared times negative sine of theta squared, which is sine squared theta. Okay, then I get 2 times the first thing times the second thing. So plus 2 times f of theta times f prime of theta times sine of theta times cosine of theta. And then I have this negative right here that needs to go out front. So this is going to become a negative. Then I get the second one squared plus f prime of theta squared cosine squared theta. Okay, So that's the first one. Now I need to square this guy. So I get plus, hopefully I can squeeze this all in, f of theta squared cosine squared theta plus 2 times the first times the second. This one's actually positive. So plus 2 f of theta f prime of theta sine of theta cosine theta, and we have a little bit more here, plus f prime of theta quantity squared sine squared of theta. Okay, and that's it. So the square root is still kind of continued over this guy, d theta. All right, so we need to combine all these together. And so what do we get? All right, so I've got a minus 2 f of theta, f prime of theta, sine theta, cosine theta, and I've got a plus 2 of that as well. So that cancels this guy. Okay, does anything else really cancel? No, but I've got an f of theta squared sine theta, and I've got an f of theta squared cosine theta. Those two combined together give me, I've got integral from alpha to beta of the square root of this one together with this one is just f of theta squared. And then this guy, f prime of theta squared cosine squared theta plus f prime of theta squared sine squared theta is just f prime of theta squared d theta. And this is my arc length formula for polar. Okay, so if you have a polar curve, f of theta, the way that you'll take the arc length is you integrate from alpha to beta of the square root of the original function squared plus the derivative of that function squared d theta, and you'll get the arc length in polar coordinates. So that's kind of cool. Okay, I think you're ready to do some homework. I will see you next time.